very excited to have Ben Recht here today from the other UW, University of Wisconsin, where he's an assistant professor of computer science. He's also affiliated with ECE, math, and statistics there. So he has quite a broad touch in the university. And in addition to that, he's one of the PIs in the Wisconsin Institute for Discovery, which is in a way related to our own eScience Institute. So he got his bachelor's from Chicago, his PhD from a small East Coast school, and then went on to a postdoc at Caltech. And since that, he's been having a rocket career, doing tremendous work in large-scale machine learning, statistics, and optimization. And for that, he's received a number of distinctions, including an NSF Career Award and the Lagrange Prize for Continuous Optimization. So with that, thank you for coming.
Thank you, Carlos, for the wonderful introduction. Thanks, everybody, for coming out today. So what I want to talk to you about today is a problem that, from my conversations earlier, is one that we all have. And it's kind of ubiquitous and not just us. It seems like everybody has this problem now, which is that we collect far too much data than we know what to deal with. And it's an interesting problem. More often than not, the data that we collect is, even though we collect a lot of it, it's still not enough for our purposes. It may be, we still end up with problems that are underdetermined somehow by all this data collection. And what I want to talk about today is kind of a general procedure of adding side information that we might be able to collect from various sources, mostly expert knowledge, to make these problems well posed. And so what I'm going to do is give you a few examples of how, of these cases where we collect a lot of data, even though we can't necessarily deal with the inverse problem. And then we'll see what kinds of structures we can overlay on top of them. So let me give one example that I've been thinking about a lot for the past 6 or 7 years. And I know that several of you in the room have actually seen me talk about this a little bit before, but for some reason, it's still very close to my heart. And that's the problem of how do we build a recommender system. Obviously, the classic one being Amazon, but the one I'll talk most about today is the Netflix. Netflix's system takes movies, which you've seen, asks for a certain set of ratings, and then just comes up with some way of recommending those movies back to you. The other case that's even just as prevalent as kind of product recommendation has been kind of matching people. Here we collect not every single thing about you personally, but based on some kind of partial answering of some kind of survey about what you like and what you're interested in, we try to find your soulmate. And so I've actually been recently convinced that the algorithms that these guys run are quite powerful because my sister met a really nice guy who she's married to now on Match.com. So the question is, how do all these systems relate to each other and what makes them work? What is it that allows us to get a very sparse snapshot of your preferences, whether it be for movies or for products or for people, and actually to have good, successful predictions of what you might prefer, given that you didn't answer those questions? Okay? And so this is really concretely codified by the Netflix prize. And actually, this was kind of what got us interested in this problem to begin with, mostly because they offered a lot of money. So it's always a good way to get people interested in your problem, offer them some payoff. And here are the 7 winners of the Netflix prize. These guys devoted about 3.5 years of their life to this problem. And so you could do some economics analysis on this, and I think Netflix wins. The thing is, not only did they get the effort of these 7 guys, they got the effort of thousands of people who competed. So it's actually, they learned a lot about machine learning, a lot about data analysis, and it's actually just a really wonderful, simple problem to state. Basically, they give 100 million movies, right? They gave 100 million ratings, right, on a scale of 1 to 5. And just the goal was to infer some 3 million that you didn't see. Okay, so they just tell you which movies, and you want the scores. Okay, so let's see how this is kind of one of these canonical examples of being a lot of data. I mean, 100 million, okay, maybe that's not a ton of data on our current scales, but at the time, to me, before I really was a computer scientist, 100 million seemed like a pretty big data set. On the other hand, there were 17,000 movies in the database and 480,000 users. And so if I multiply those two together, the full table has 8 billion numbers. Right? If we want to specify the full model, it has 8 billion numbers. Yet I'm only seeing 100 million. And so the question is, what exactly can I do to fill in those blanks? Okay. pretty easy to state. And we can even abstract away the Netflix layer and get down to something even more primitive, which is the problem of matrix completion. Okay, so in matrix completion, now I have a data array. I see the entries that are colored in black, and the majority of the entries I just don't observe. And so the question just becomes, what do I do to fill in this missing data? Okay, so now if I don't tell you anything else and we just stop there, there's not much we can do. I mean, what are you going to do? You have to assume something about what's in the white area in order to make this problem well posed. And now just the question becomes, what's a reasonable model? Okay, a standard and kind of ubiquitous model is using the fact that if this is generated by people, then perhaps this matrix is well modeled by what's called a factor model with very few number of factors. This is basically just saying that your taste in movies aren't as unique as you think they are. So the hope is that the majority of your preferences can be summarized by figuring out what type of person you are or how much you correlate with a given set of types, and just finding out your weights there, and then we can make the prediction. So if we actually knew these two factors, we can make everybody's prediction. This is kind of a canonical model in statistics. Now, what's nice about that model is the number of entries is much, much smaller. Right, so on the one hand, you have 8 billion, that's the k times n. On the other hand, we have something substantially smaller. And if r is in, let's say, the 20s, we might have about 10 million parameters in the L times r. But we had 100 million observations, so it actually looks now that we have a well-posed problem, or at least an overdetermined problem. And now the question just becomes, can we actually find those factors when most of the data is missing? So that notion, what did we do there? We found a notion, which in this case was this how many latent factors there are. And that's what's called rank. That's called the rank of that data matrix. And rank is precisely how many latent factors are enough to well describe that matrix. So in this case, we used rank as a way of summarizing the simplicity of a matrix. It's kind of this proxy for saying that that matrix is relatively simple and has less entries or less parameters than it might appear. And rank actually is a really powerful model of simplicity. It comes up, for example, in embedding problems. So for example, if we were trying to find the geometrical shape of a protein and we only knew some interatomic distances, we don't need to know all of them actually to recover it, because the matrix of distance pairs ends up being related to a low-rank matrix, something called the Gram matrix. You can transform that distance matrix into a Gram matrix. And the rank of that Gram matrix will either be 2 if your thing is in 2 dimensions, and 3 if it's in 3 dimensions. And if somehow if you live in 26-dimensional space, like a string theorist, then it's 26. In machine learning, you might actually use the notion of rank to say when you have certain tasks that are correlated together. So for example, if I had the task of recognizing digits, they might have specific ones tailored to each individual person, but then you know that, for example, the letter A should be somewhat similar to classify from person to person, because there is some similarity. And for my electrical engineering friends in the room, the other place where rank really comes up all the time is in dynamical systems theory. So if I have some time series, it turns out that you can arrange your time series data in such a way that the rank of this matrix that you get out is actually equal to the number of parameters I need to predict the future. This is called the dimension of the state. And so this has kind of been used in controls as a way of, actually by a couple of people I actually know in the room who have worked a lot on this, using controls as a way of kind of reducing the order of the complexity of a control system, or ways of actually summarizing time series data. So it kind of puts this together. There are a lot of cases that we can come up with where we'd like to solve this problem of finding the lowest rank matrix that agrees with some data. And like the simplest version would just be, find me the lowest rank matrix that agrees with some equations, linear equations. Okay, so the simplest one is, these are the entries on some subset. But it could be much more general, as we saw in those other cases. The problem with this problem is that it's hard. Minimizing the rank subject to just linear constraints is NP hard. Seems simple, actually is quite challenging. Basically, there's a variety of reductions you could do. Simplest one might be saying that that's a quadratic system. So in solving polynomial systems is hard. Turns out that it's also hard to approximate. And there are actually exact algorithms from computational geometry that basically work up to matrices of size 5 by 5. This is not an insult against computational geometry. They're useful problems that are size 5 by 5, but it's not exactly a big data problem. So the question really becomes, what can we do? I feel like the prevalent notion in computer science theory, maybe up to about 10 years ago, would be saying if it's NP hard, we can go home. Right? That's the end. You show it to your boss and you get to go home. That's actually, I'm kind of joking, but that was actually in the preface of Gary and Johnston, the first book on like NP completeness. They actually use that as somehow as a jokey excuse for why we care about NP completeness, as a way to kind of excuse us from working on them. But of course, since then, there's been a lot of work on heuristics and approximation algorithms. And the question is, what can you do if I have a problem and it comes to you and I say it's NP hard, what's the right thing to do in that case? Because if someone's offering me $1 million and the problem's NP hard, well, maybe I still would like to try to solve it anyway. Okay, so what would I do? So one idea that's actually been quite prevalent, I'm not going to go into the details of it just yet because there's a simple algorithm for actually solving this problem, is minimizing something called the nuclear norm. We replace this rank function, which you saw in the previous slide, with a surrogate. There's something called the nuclear norm. I'm going to talk about that a little bit more in more depth. You have actually one of the experts on this norm, one of the people who really popularized this, Marianne Fassel, on your faculty. But here, let me just give you the algorithm that you can use to actually solve that problem, which is we're replacing something that's hard with something that's easy. And not only is it easy, look at the pseudocode. What you do is you pick an entry from your corpus. Right? I have all these entries that have been revealed to me. I pick one. I compute how wrong is my guess. So I have my factors L and R. I just initialize them somewhere. I'm sorry, I always forget that the laser pointer doesn't work, so I'll just point. I have my factors L and R. They've been initialized somewhere. I make a prediction for what M should be. I compute my error. And then I have some parameters, alpha and beta, and I just compute this step. Right? That's the code. You can write that C code, and you will solve the Netflix prize. Well, not exactly, but I'll show you in a second that that does really well. This simple thing is actually solving that much more, somewhat more complicated problem in state. And you can actually prove, and I proved with several collaborators, that basically as long as the number of entries that are revealed is on the order of the number of actually true parameters, this heuristic will work. It'll actually solve that NP hard problem. So this was work that I did with Mariam and Pablo Perillo, also followed up by some work with Emmanuel Candes. And actually, I posted the third citation as some guy on LiveJournal because that actually, there was the first publication on how to win the Netflix prize was just some dude writing on his Netflix journal, on his LiveJournal page. He proposed basically this scheme. Now, we can't really give him credit for this scheme because that, there's a statistics paper from 1974 that proposes the exact same thing. But that's all right. It's all right. This is research in the blog age. We don't have to cite. But what he did manage to do is to actually get up to a 6.5% improvement on Netflix just using that heuristic. So it's actually that the theory and the algorithms coincide exactly there. And the guys who won did some mixture models of a few 200 some odd different variants of this, and they combined them all together and parameter tuned for 2.5 years. So basically what happens. So there's a good example where we had something, I think this is a nice canonical example, but there are others we can come up with. Let me give you another example of the specific case that I worked on that becomes something a little bit much more popular that you'll recognize in a moment. Okay, so let's completely change gears. Let's forget about recommendation systems. Let's think about the problem of just looking for biomarkers, which you guys may be familiar with. I got interested in this problem talking with some cancer researchers at Stanford. So they had this very interesting model where they could actually give rats, pregnant rats, a carcinogen. The rats would basically bear offspring that looked exactly like control groups, but somewhere in this green region, here we have basically days. This is day, the E17 is like basically when the carcinogen was born, 17 days before birth. P1 is when they're born, P180 is when they die. In the green region, they would look exactly the same as the control group. Completely indistinguishable. In the red region, they would die. In the yellow region, at the very beginning, you wouldn't be able to see a tumor on the microscope, but these tumors grow exponentially quickly. So by the end they get to this yellow region, you would actually be able to see a brain tumor using MRI. Okay? But if you killed the rats earlier on in this cycle and you cut up their brains, you would actually see little tumor nests, things that you couldn't see with an MRI, but they were definitely there. And kind of the overriding kind of mantra of cancer treatment is that if you can detect it earlier, you can likely treat it better. By the time you actually see it on imaging, this is a particular type of tumor called glioblastoma. By the time you see those things on imaging, it's far too late. And by the time you develop symptoms, it's far too late to treat. So the question is, could you see it earlier? could you screen for it earlier? So the folks I was talking to were very interested in doing something called mass spectroscopy, cell-D mass spectroscopy, to find markers in these rats at the kind of end of that green region. And so they would take these rats, they would look at blood, and they would look at spinal fluid, and they would just get plots that look like this, scattering of, of many peaks, and they would actually end up looking for which peaks are the most relevant for that distinguish the control group from the study group. Now, you learn a lot of things working with biologists. One thing I learned, rats are incredibly expensive. So the number of rats that we could actually train, that we could actually give this carcinogen to was sadly very small. It was about 40 over the course of about 2 years. And that was tens of thousands of dollars. It's kind of very expensive. So we actually ended up with something where we'd have hundreds of peaks and only a few patients, 40 patients. So we're in exactly the same problem we were in with the Netflix Prize problem. We have much less data. We have much less samples than the total number of apparent peaks. But there's hope, maybe, if there are only a few of these peaks are actually important. If you're in the case that there are only a few of these peaks are actually relevant for diagnosis, it's good for two reasons. One, statistically, there are very powerful tools, including something called the lasso, which hopefully my statistics friends know very well, where we can actually find a sparse set of markers that can distinguish these peaks. Moreover, as the doctors will tell you, you cannot get away with some kind of screen that requires looking at hundreds of peaks. You need something to connect it back to the biology. And so you need that simple explanation if there's any hope of actually coming up with something that can get approved by the community. So we ended up actually doing this study, and actually in a recent paper that we published in PLOS One, we're able to, just using these statistical tools, extract out a few peaks that were relevant, and we're hoping that we might be able to actually get an early screen for this kind of cancer. There's been a lot of action in sparsity. So I think the place where you may have heard more about these methods, where you have a signal that is actually sparse, where the number of components that are non-zero is very high, is in something called compressed sensing. Unless you're the statisticians, because all the statistics people actually know this from the different name of the lasso. So in compressed sensing, the idea is that natural images, under the right representation, are incredibly sparse, have almost no content in a lot of the bins. So what I'm showing here is a picture of a guy taking an old-timey photo. I think it's from the Caltech 101 database. My vision friends probably could correct me where that's from. What I love about this is for people who've been to MIT, this is not taken from 1910, because the green building that's up here, that was built in like 1980. Anyway, I don't know what's going on with this picture, but it's the cameraman picture. It's canonical. So if you do something called the wavelet transform, or you do a wavelet transform of this image, you get a heat map shown over here. So blue in this picture is 0. Everything red is big. It's a large peak. You see it's mostly blue. So images actually are low complexity if you look at them the right way. And wavelets are actually the way that people like to use them. And so the idea behind compressed sensing is that if we, what we typically might do would be to take the picture, do the wavelet transformation, throw away all the things that are 0 and store that. That would be called JPEG compression. But what we could do is actually only acquire a number of numbers corresponding to how many peaks are active. We can actually acquire that faster. And this has actually been, had a lot of impact in MRI, where, because I don't know if anyone's had an MRI, being in them is a little bit traumatic. And especially in pediatric care, it's hard to get a kid to sit still in a pediatric MRI. And so being able to acquire this faster, be able to acquire an image faster by taking less measurements, has a huge impact on the amount of trauma you inflict on children, which is always good. What's interesting is that the whole field of compressed sensing was made by noting that we can take another NP-hard problem, replace it with something simple that we can solve, and exactly extract out that information. So I just want to say it has the exact same structure that we looked at before. We want to find a sparse solution to a set of linear equations, just like we had before, finding a low-rank solution to a set of linear equations. This problem turns out to also be hard, and provably hard in many of the same ways that the rank problem is hard. And the heuristic of just replacing this function of counting how many non-zeros there are, minimizing the number of non-zeros, to replacing it with minimizing the sum, the L1 norm is the sum of the absolute values, you have something that 1 can be solved with what's called linear programming, 2 can be solved on really big things like images, and 3 actually is kind of the heart of this compressed sensing. What makes it work is you can prove that this works. You can prove that this is always going to give you exactly the number of measurements you need is proportional to the number of non-zeros in the wavelet transformation, not the total number of pixels. Okay, so there's this latent structure. As one more example, something that I actually just put this in for you guys. I'm not sure if any HCI folks actually came, but I had a brief stint of being an HCI guy when I was at that small East Coast liberal arts school that I went to. So I worked with one of Hiroshi Ishii's students on a project called AudioPad, which was kind of a RFID tag-based interface for doing electronic music. They let us do a lot of things. I went to the media lab. It was kind of like going to Montessori grad school. So I got to do machine learning. I got to do HCI. You know, you figure out what you're doing as you go along. So this is James's hand. That's me. This was actually a really fun project. We actually got to make really cool sounds. We got to go to present it at the Ars Electronica Museum in Austria. But what was interesting, so this is James's platform that he built. It had a lot of different applications. You know, you could use this kind of interface for a variety of different things. And basically, in that tabletop was a special antenna. That special antenna basically measured the signal strength of those little objects that was on top. That actually corresponded to, they were just little LC resonators. And you would get from measuring the kind of output of these antennas this kind of crazy path that looks like this. I mean, this is basically the output as I just move from left to right across the table. And James spent, I don't want to downplay, about a year engineering a system to figure out how we go from the XY position to, well, how we go from this stuff to XY position. Okay. So in some work with Ali Rahimi, who many of you may know because he was at the Intel lab here for a little while. Well, we figured out that there's, in a lot of these HCI systems, kind of a common problem, which is that you have really complicated forward models for how you go from a little signal to kind of just picking out where somebody's hands are. But the thing is that the people's motion always kind of obeys Newton's laws. So what we could do is actually leverage the fact that people are moving to actually infer these forward maps. Infer these inverse maps to 2D positions without knowing anything. And actually, we just using the same model for this kind of audio pad, as for articulated tracking in video, as for something that Josh Smith built when he was a PhD student at the Media Lab as well, we could actually infer these kind of articulations just using the fact that we knew that people were interacting with it, mostly because they followed dynamics. Following up on this, I've actually been doing a lot of work on time series. Right? And so time series, basically what you have is you have some input data, you have some that's driven by something U, and you see some outputs. And basically what we treated the ACI problem as inverting a time series problem. More recent work I've been doing is using very similar techniques to try to extract out useful features in exercise testing. This is something I got into while I was at Caltech because it turns out that everybody there is into triathlons, so I had to keep up. This was some work I did with John Doyle, and we actually managed to send out late last year. The idea was that if you drive a human via putting them on an exercise bike and making them do weird hill workouts, you can actually infer a lot about their kind of their health and the state of their health by kind of correlating the way that the input maps out to the output, which is the heart rate. So you can look at the heart rate and their oxygen production and map that against watts, and you can actually infer out who is actually a healthy subject and who is maybe unhealthy, and how can we maybe design an intervention to fix that. This kind of problem of kind of inferring some model from these time series data for very complicated underlying processes has other applications. For example, when we actually look at building live cell models of kind of protein networks, oftentimes what we're allowed to measure, we have a very simple set of stimuli and a very simple set of responses, and we would like to infer things about very complicated protein and interaction networks. And again, what we can do is try to just leverage this kind of like black box time series models to get at what actually works and doesn't work in these kind of systems. And another place where this is huge, time series analysis probably is most used and kind of the most money is generated, is in predicting stock market and high frequency trading. in that case, what you do is you use the fact that actually on very, very short timescales, not the ones I've shown here, that's at an hour granularity, which is actually much too slow. But on the minute granularity, you can actually predict these small trends, again, by looking at what happened with the past inputs and how they were derived to the future. So this is another one of these problems where we have a dynamical system that we're measuring. We're seeing the time series data, and we would like to actually build some kind of parsimonious mapping from the state, the driven input, to that output. And the system identification problem, which I kind of briefly hinted at earlier, is really just finding a model that agrees with this time series data, whether that be that something that I'm interacting with in an HCI or some kind of much more complicated biological system or something that arises in the stock market. And what you can use in this case, what's the latent notion of simplicity, is that actually all linear systems are just a combination of very simple things called single pole filters. And in some recent work with my postdoc and a couple graduate students, we were actually able to design new algorithms, again, just using the fact that we have this latent dynamics. So in all of these cases, we had these very complex systems that were churning out a lot of different kinds of data through experimental models, through time series, through interactions with web interfaces. We would like to kind of pull out some kind of reasonable predictions from these things, although the problem was still underdetermined. And what we had to do is leverage some kind of structure to actually make that problem well posed. And that structure could be either rank, that could be sparsity, that could be dynamics. So what I want to now bring us all back through all these examples, so that how do we kind of codify this problem? How do we actually analyze how well we can do? And finally, how do we actually build algorithms to do it? I'm just going to give you the high-level picture of how that works. So you saw this slide 3 times. I'm going to show you to you one more time in the most generality. The linear inverse problem is just finding a solution of a system of linear equations, which I hope everybody here has done at one point or another in their life. That if I have a system of equations where the number of rows is less than the number of columns, if I have one solution, I have an infinite number. So if I have an infinite number of solutions, which one do I pick? Right? And this is where we come in. In all of these cases, we have to ask the domain experts what is a reasonable answer to come out and leverage that kind of structure that underlies it. So that structure could be sparsity, rank, some kind of smoothness or dynamics, some kind of symmetry. If we can codify which of these structures are actually underlying the X we want, then the question is, how do we actually design an optimization problem to extract out that data, to extract out that X? So what I'm going to do is go through the examples that I went through earlier and just see what is the geometry that underlies all of these kind of good heuristics that work. What actually makes them kind of ties this all together? So this is the case of sparsity. This is kind of the compressed sensing problem. This is all of the sparsity 1 vectors that have norm 1 in 2D. Unfortunately, I'm going to go through the proof of kind of our theory via cartoons, so everything's in 2D, but hopefully this gives you all the salient features that you need to understand this. Here is the things I think are most simple. And if I color in the region between all this stuff, what do I get? I get this diamond shape. And that turns out to be what's called the unit ball of the L1 norm. Okay, now, if I want to, here's an optimization problem that I might want to solve. I would like to minimize the L1 norm, which is just the sum of the absolute values, subject to linear constraints. So I have something that I know is true. I would like to actually minimize this kind of penalty function subject to these constraints. What does that mean? It means I take the unit ball of the norm and I blow it up until it touches the line. And what do you see? Lo and behold, I got a corner. Okay? This picture I stole directly from the first paper on compressed sensing by Candes, Romberg, and Tao. I mean, this is in that paper, and this kind of describes why this algorithm should work. Okay, so how about rank? We could do the exact same thing in rank. Okay, so again, only simple pictures. So in this case, we have x, y, y, z, norm 1, and it's these 2 circles. So I can color in the region between the 2 circles, and I actually end up getting a norm. Okay, so what is the norm? It's a little weird, and I guess only for the folks who know some numerical linear algebra, I could tell you what it is. It is the sum of the singular values of the matrix. Singular values are basically, if you don't know come ask me later. I'm going to be very disappointed if you don't know. So. But singular values are essentially they're analog of eigenvalues. They're the square root of the eigenvalues of XX transpose. Okay? So but the point here is that the convex hull is a function that we can compute. It's a function we can minimize efficiently, and actually it was kind of the basis of that blog heuristic I told at the beginning. And what you see again is that even though I have this full blue region, the corners are the low-rank matrices. So if I minimize this norm, subject to equality constraints, I'm going to hit on a low-rank matrix, pretty much generically. And this is kind of the heart of why this was a good heuristic that was proposed in Merriam's thesis. Also kind of was kind of the basis behind our first paper on this subject, and it's kind of followed up with this whole theory of matrix completion, all kind of based on this idea. Okay, I can keep going. I'll do one more. Okay, integer programming. Okay. In this case, the corners are just, let's say, are just binary vectors. We'll do a really simple integer program, like a multi-knapsack. So the corners in this case are 1 and -1, and we have some linear constraints, and we'd like to solve that. When I color in the corners, I get the infinity norm. And now I get the simplest linear programming relaxation of this integer program. And again, it's just derived from me automatically. The intuition is exactly the same. I generically should hit on the corner. And using, again, the same kind of analysis with Mangasarian, we were able to actually prove conditions under which this heuristic worked for the multi-knapsack. So what ties these all together? Well, we have a model that we want to fit. This is the solution that I want. There are some kind of atomic building blocks that kind of underlie the model. And we know that we can come up with a combination of those models that has some kind of short sum. We have a very short sum that sums up X. Okay. And these atoms here could be a variety of things. They could be a discrete set. They could be the set of low-rank matrices. They could be the set of all single-pole filters, like we said. And the idea, or kind of the meta-algorithm in all of these cases, is to minimize the sum of the absolute values of the weights. All of these cases amount to this. Minimize the sum of the absolute values of the weights, subject to having that decomposition hold. And in the case that the atoms are just kind of the standard basis vectors, this is the L1 norm, and it looks like the L1 norm, but these atoms can live in a very complicated set, and actually this will rederive all those other heuristics I just discussed. So we call this thing the atomic norm, and what I kind of want to, so now again, this is only because I'm a fan of bad puns. We had the nuclear norm, or the work we did with Merriam. Obviously, that would be the next step. So which way is that going? That's going out. So I guess the next one will be the molecular. Yeah, okay. And so in a recent paper with Venkat Chandrasekaran, Pablo Perillo, and Alan Wilsky, we kind of codified a way to do two things. One is actually use this atomic norm to analyze how many measurements we need, or how many samples we need to actually recover models that are simple in this way. That's thing one. Thing two, give a generic set of algorithms that kind of actually solve this problem. So I'm going to talk about both of those in turn. Actually, before I do that, let me just say that you can get a variety of fun algorithms out just from using this framework. So one thing that we looked at was the problem of looking at where my signal might arise from a union of different subspaces. This is something that arises in kind of like a lot of image matching and kind of texture mapping. It also arises in wavelets. And in this case, you can actually solve this problem with something called second-order cone programming. Another problem that's kind of always of interest when you're at school with a good football team is rankings. I don't know, actually, I guess it's mattered less here recently, but who knows? You never know. You never know. But in this case, what we might have is that we have a matrix that we would like to, or we'd like to infer some ranking, and we can model that as a matrix, which is a sum of a few permutation matrices. And that one we can solve again by linear programming, because the convex hull of all these permutations is actually well described and well solvable by linear programming. And there are a variety of other things, obviously, I could spend a lot of time talking about that we've been looking at, where, again, you come up with a model of simplicity. It could be kind of a problem of moments, a problem of clustering, a problem of tensor factorization. And then you actually just apply this framework. You see that there is an algorithm that will come out that you can solve. And then the question just becomes, how do you analyze it? We'll go through one theorem which actually kind of demonstrates how we actually derive all of our measurement bounds. And it's based on the following thing. And this is why these kind of convex heuristics are nice. These convex optimization heuristics are nice. We can characterize when we have a good answer. Okay. So if I look at this problem, I minimize this atomic norm subject to some equations, then I know I'm at the right solution if for every direction that moves away from x, so these are all the guys such that basically you don't get any information from the data. So all the things that are hidden by the data, all they're going to do is increase the norm. They're going to make the norm bigger. If that's true, this is kind of tautological. That's the nice thing about this kind of mathematical statement. If that's true, then x is the minimizer. Okay. I have x. I look at all the directions that make the norm smaller, and I note that they don't coincide with all of the directions that keep me in the feasible set, in the set of equations. You just want to basically show the intersection of all those red directions with all the green directions is 0. It turns out doing that is not so easy, but we actually had to rely on some pretty heavy machinery from Gaussian process theory. But in doing so, we were actually able to derive nearly optimal rates in a lot of the cases that we looked at. So for example, again, this is only for the few experts who are in the room who've seen these things before, we derived optimal rates for both the hypercube and sparse vectors. And we do this in a non-asymptotic setting, basically saying that you get down to the minimal number of measurements you could ever get using any algorithm. This convex algorithm actually does the job. Something you could solve does the job for a variety of cases. And then we also looked at a variety of other models. For example, the matrix completion problem, where we actually get down to a factor of 3 from just the number of numbers you need to write down the matrix. Again, this is then under the case of a kind of randomized analysis. So this doesn't say you could solve it in general, because obviously we can't, but it's saying in most cases, the number of equations you need is proportional to kind of the number of parameters that specify that model. Okay, so that's great. So now we have two things. We have a nice way to kind of tell practitioners how much data they need to collect, how much data do you actually need to specify your model. And now the second thing we need is let's solve it. Let's actually find ways to solve these things quickly. Now we have two things. We have a nice way to kind of tell practitioners how much data they need to collect, how much data do you actually need to specify your model. And now the second thing we need is let's solve it. Let's actually find ways to solve these things quickly. This atomic norm minimization, what's cool is that we generalized a lot of things that we already knew. We came up with new algorithms that we didn't know before. We have a nice way of actually generating really good tight bounds that tell our practitioners how many measurements they need. And the thing that's kind of cool is that we can come up with one algorithm, and that's what I want to close with, one algorithm for prototyping all of our data mining problems. And that's kind of, so this is kind of like the computer science part of the talk. We have now an abstraction, and we can just optimize that one abstraction. I mean, optimize in the sense that you guys are familiar with, maybe not in the sense of running a numerical optimization problem. So let's look at that. Let's go through a couple, just an example of exactly how this kind of prototyping works. Okay, so all of our problems end up looking something like this. We'd like to minimize a function where we have basically terms that depend on the data, these f sub j of x. These could be least squares differences. These could be misclassification errors. I'm going to make it very general at this case. And you're going to add that to the norm. And the norm is basically going to try to preference you towards being at one of these simple points. Okay, so all of the cases we looked at so far, basically you had these things being as equations. We're now going to add to the case where we can do the robust kind of data mining algorithms. Okay, so here's an algorithm that will solve that problem, no matter what you do. This is really nice. Basically what you do is you pick one of the j's. You take the gradient of that one j, meaning you compute the local direction that's going to most improve just that one component. And then you take a step along that, about that improvement direction. And then you apply something called the shrinkage operator that's associated with this norm. Okay? So if you could compute this thing, if you compute this shrinkage operator, then basically now we have, that's the only thing that changes as you go from structured prior to structured prior. And most of these have kind of nice, compact ways of computing them. And so what's cool about this, and this is something this is what I learned by being in the computer science department, is it has this nice computer science flavor that once you have identified this one algorithm, we can actually figure out what are the primitives that we need. This is something that's taught to me by one of your alumni, Chris Ray, very well-trained guy, about what exactly are we looking for in a good algorithm that can be robustly deployed. What do we have that's nice? One, the memory footprint is very small and very predictable every time. Just by the nature of the theory of this algorithm, it's robust against noise in the data, and essentially achieves what are nearly optimal learning rates under a variety of settings. And the other thing that's nice is it's one algorithm, so we don't really have to change too much to implement it. Right? We just want to implement one thing. So in work with Chris, we actually showed that you can actually implement this in a standard relational database, basically by adding one user-defined function and then using some stuff that are kind of native to most of the database programs. But to make it really scalable, we started to look at what can you do to parallelize it. And this was work with Chris and Stephen Wright and Feng Nu at Wisconsin. Okay, so the question just becomes, is this stochastic gradient descent algorithm inherently serial? Or can we actually use the fact that we have multi-core computers on every desktop now, or probably everybody's laptop? Can we take advantage of the ubiquity of cores? There's been a lot of activity in parallelizing stochastic gradient descent. Most interestingly, that the majority of it was done in the 80s. But of course, computers were different then. But actually, it's always amazing to me when you go back and look at distributed numerical computation that was proposed by Bertsekas and Ciciclis. Most of that we're just always reinventing. There's so much stuff in their book. But so yes, there were a variety of other procedures. Actually, a lot of them were actually in Bertsekas and Ciciclis' book. Doesn't matter. All of these things actually, when you tried to implement them, suffered from something that kind of always was what kills large-scale parallel algorithms, and that's that they all kind of need the processors to talk to each other. Okay? And as soon as you actually have to communicate, all of your parallel wins go away. And actually, if you looked at, we downloaded the second code, and we ran it on some of our problems, and as you added cores, it took longer. Inspired by work that was done at Berkeley on kind of like minimizing communication in linear algebra, we wanted to see what do you have to do to minimize the amount of communication to parallelize stochastic gradients. And the idea actually ended up being very, very simple. This was something that was proposed by Chris's graduate student, Feng Nu, was he just took out all of the mutexes. He just took out all of the locks and just ran it anyway. And lo and behold, that works. And that's the basis of our algorithm, which we call hog-wild. Each processor basically independently runs stochastic gradient descent without talking to each other and with overriding each other possibly. Basically, all they're doing is, I wrote the pseudocode on the previous slide, right? They're just running it independently without talking to each other. And in our analysis, we kind of assume that you can atomically take a memory location and add a scalar to it. So we're assuming that one operation can be done without a locking structure, which is true on most hardware. Now, the issues here is that they're running asynchronously. They're not talking to each other. So you can have very old updates. You can have overwrites. And the question is, when does it work? And in our paper that we wrote in NIPS last year, we actually showed that overall, this doesn't kill you as long as the overwrites are somewhat sparse. And in practice, it turns out this actually works really well. On a variety of data sets, on a 10-core machine, well, actually it was 12 cores, with 2 cores just for data management, we were able to get very fast speedups. We were able to get nearly linear speedups on a variety of problems that were on the gigabyte scale, just running this algorithm. And so here are some of these curves. So now the next question is, you look at this kind of plateau in this third curve, and you think to yourself, what else can we optimize? This is always kind of the fun part. We have one algorithm, but we can get more specific. And what I would like to close with is try to figure out what is going on in that last guy. What's going on in that last curve? So in that last curve, what we're seeing is saturation, basically because we had cache coherence issues. And so the final thing that's really nice about kind of all of this, using geometric structure, is that not only could we use it to kind of design new algorithms and design new norms, we can actually take advantage of that structure in the actual processing, in the actual implementation. And that led to this final algorithm, which we call the JELLYFISH. So remember, I'm just going to skip ahead a little bit here. Remember, there was this ridiculous heuristic that was proposed by our friend on Live Journal, actually, well, fine, proposed in 1974 by Axel Roux, which is we just are going to incrementally pick a matrix entry, compute its dot product, and use that to update our equation. Right? And that's basically solving, you can actually go back and check, that's solving this kind of nuclear norm problem that Mariam and I and others have studied. You could run hog wild just to do this kind of problem, but there's actually extra locality that you can take advantage of in the particular structure of matrix completion problems. So what you'll actually see is that if I actually write out, let's say I just partition my L and R into these 3 chunks, if I didn't have any entries in kind of like the off the main diagonal, I could run it completely in parallel. And similarly, if I only had entries in these check boxes, I can run those completely in parallel. And finally, if I only have entries in the white boxes, I can run that completely in parallel. So the algorithm, the jellyfish algorithm, just does that. It imagines like that's the case, and in sequence runs the gray blocks, the square blocks, and the white blocks. Okay. And you first pre-process the data to put it in a random order so you don't introduce biases. Okay. And it turns out there's no locks here, and there's no collisions, because everybody, not only do you not have to communicate, but you're never going to overwrite. Everybody's actually just doing serial things that seems like they should work. And when we run this, well, so this was my first surprise. It's actually kind of a little bit out of order. We compare against other algorithms, like things in MATLAB, and you would get 100 or 200 times speedups over the standard solvers. We were getting actually very similar speedups over algorithms that were based on the singular value decomposition, which is something that kind of most of these matrix completion problems were built on. And what's nice is that this thing actually seems to keep improving as we add more cores. So on our 40-core machine, we're doing significantly better than our 12. When I presented this at a workshop, a compressed sensing workshop, this actually led to another collaboration, which I found very interesting, with some guys at University of British Columbia. We presented this algorithm, and this fellow Felix Herman came up to me and said, well, I think we can actually use this for a particular problem, a particular inverse problem. It's the following. Basically, there's this idea of trying to look for oil or minerals or just basic stuff in the earth that works in the following way. You take a ship, that ship kind of goes over the ocean, it transmits a little low-frequency pulse into the Earth's crust, and it has this trailing of receivers, this little, drags along a bunch of these receivers, receiving basically these reflections. And you get all these kind of different scattering off the Earth, you get that back, you get your full big array of data, and from that you're able to actually invert the structure of the Earth using basically PDEs. Kind of complicated story. Now the thing that's weird about this problem is that these guys legitimately have big data. Very simple seismic surveys will get you terabytes of data. And if you're willing, and if you actually, what the oil companies really want is to go bigger. I mean, they can easily generate petabytes. Because if you think about it, what you have is a location of a transmitter, that's two numbers. You have a location of the received wave, that's 2 numbers, and you have time. So we're dealing on these things that even if you have a granularity of like 1,000 samples in each of these coordinates, now we're seeing it's getting pretty big. So that's complicated not only to work with on one of their server farms, but it's also really painful and tedious and expensive to collect. So one of the goals was actually now, okay, well, what else can we do? Well, we're going to, what we can try to do is sample this sparsely. Actually only samples to take a very partial survey and then use some of these matrix completion techniques to fill in that sparse data. And in fact, it turns out that the PDE itself has low rank structure. And so in joint work with Felix Herman, we've been looking at these kinds of things, hopefully you can see in the back here, where we would actually only get partial snapshots. We use a particular arranging of the data from our partial snapshots and run the jellyfish algorithm. And we're actually getting state-of-the-art results in this kind of impartial seismic inversion problem just using this algorithm we developed. And so this is a great example of the really nice feedback loop that happens between kind of the mathematical foundations of data analysis, the algorithmic implementations, and then the applications. So we kind of went through this story where we went from applications into theory, implementations, and then through a serendipitous meeting with some folks at British Columbia, we actually came up with yet another application. And there's actually interesting structure that you can even leverage here. So moving forward, what the kinds of things that, that I'm interested in doing is actually looking at more structures, whether these structures come from tensors like that arise from PDEs, or more complicated interactions with human physiology, or kind of things like that arise in non-negative matrix factorization. And then taking these kind of structures and measurements, scaling them through new algorithms that kind of exploit these structures, and then hopefully learning from our practitioners who we're working with in collaboration what actually has to be put back in to refine the theory. I mean, this is kind of like very intricate. It's not an open loop process to actually do this discovery, and it's kind of critical to actually be able to kind of close that loop and go through that process. Okay, so with that, I just realized that these things are out of order. I'll close there, and I'd be happy to take any questions. And again, thank you for your attention.
I'd like to open to any questions that we have.
Yes. What do you give up by removing the blocks?
What do you give up by, that's a great, okay, so you give up a little. Now you can have overwrites and you can have delays. So we can actually quantify based on the maximum length of the delay, and with actually no assumption about the overwrites, exactly how much you give up. But what ends up happening in practice is as long as basically the problem structure is very sparse, that's negligible compared to the speedup that you see. So you can actually quantify very precisely in terms of that maximum delay and basically the possibility of overwrite, how much you would lose. But it's actually dwarfed by the parallel speedup.
What guidance do you have for picking the norm and thinking about how to structure my problem, the prime partition, let's say?
I just realized that I was told that I was supposed to repeat questions. The first question was what is lost by removing locks? The second question is how exactly do you guide the development of new norms? For the most part, that actually has to happen with a conversation with the practitioner. So these kinds of things are actually hard to do in a vacuum, and actually completely impossible to do in a vacuum. The only way that we've been able so far to basically compile new norms is to actually interact and collaborate and learn more structures. I think a great question, though, moving forward, is there actually a way to learn these norms or learn what the right penalty is to use? And so for some people who may be familiar with this in machine learning, there's this notion of dictionary learning, which is kind of a way to do this in the kind of compressed sensing land. I think that could be made much more general and would be a great problem to work on moving forward.
Any more questions? Jeff?
Yeah, I just had a question about the scalability from, say, multi-core machines to many-core machines. And in particular, when latencies and other kinds of delays become a lot more prominent, communicating all the way across the machine. And these are machines that actually are available in companies.
That's right.
How do you think it would scale?
That's right. So there's basically a two-part answer to this question that Jeff just asked, which is basically what happens as you move from multi-core to many-core. So as you move to something that's not just all based on one die or one chip to something that you actually want to have talk to multiple computers. The longer the delay, the worse that the locking is going, or the worse that these kind of overwrites and delays are going to hurt you. And so what you have to do is actually change the algorithm. And so actually a lot of the other algorithms that were already that were proposed kind of worked with that long delay model in mind. Like the round robin algorithm and some of the averaging gradient algorithms that were, actually that one won't work, but some of the, actually the old Berzekis and Sisiclis algorithm would just kind of basically transmit the solution to each other every once in a while. You can actually work at a much longer, you could actually have slow communication that actually could have them talk to each other. But the reason why we looked at multi-core, just as a starting point, was because everybody was starting with the cloud, but yet you could buy a machine with 40 cores and a terabyte of memory for, it depends on what your discount with whatever your vendor is, for like 15K. And for a lot of problems, I mean, if I could fit a terabyte in memory, I could do a lot of stuff. So it seemed like a good first primitive to look at, and that's really what motivated that. But you're right, as you move to larger cores, you guys, to longer communication times, you can just change your granularity. You could change how much information is transmitted between them, and you just want to make sure they're not waiting.
Do we have, Vernon, was there a question? No. Anybody else? Oh, one more, last question.
So this is maybe just somewhat related, but in many of those big data problems, not only the problems that the data is sparse, but often there's just a lot of wrong data, right? So what's your take on how that affects the problems?
Magda is asking, what happens when the data is wrong or is corrupted? So today I was actually really focusing, just because for the sake of simplicity, of just assuming it was missing. But you can actually extend these techniques to the case when it's erroneous. So the way that we typically do it is we actually look at the case when there's no corruptions, because even there is hard. And then from there, we actually have a method to bootstrap up to these more noisy situations. And we've looked at different kinds of noise models and actually been able to analyze those. So we kind of bring a little bit more statistics.
Thank you very much.